So we're going to be talking now about forward error correction, or FEC. And if you'll recall from the beginning of the class, we've always had these three prongs: the bit error rate efficiency, or power efficiency. We've also had the spectral efficiency. And in the last corner, we had cost. And cost, we use this as coherent detection, as being something that could be a bit more costly solution, but one that had better performance, but much more spectrally efficient. And now we're looking at forward error correction, and the forward error correction is going to come in here. It's going to be more expensive because we need extra digital signal processing in order to implement the forward error correction. But we're going to do that to correct errors to become much more efficient in our bit error rate. And it's not for free. We're going to have to balance, and that balance is going to be, we're going to take away from the spectral efficiency. So, always trying to move around and optimize. If I just wanted to throw a whole lot of cost at the system, remember we saw that capacity bandwidth efficiency plane, and I said, well, if I didn't care about cost, I could throw away all the spectral efficiency, I could get a better bit error rate, but now we're going to talk about quantifying that. Okay, so how much cost? How much less spectrally efficient? How much better BR do I get? So we had that Shannon capacity that gave us the performance. We didn't have coding in that equation. And now we're going to say, suppose we use coding, how can we actually get very, very, very close to that Shannon capacity limit on the bandwidth efficiency plane? So we had points where it was just modulation, no coding, and now the coding is going to allow us to actually improve our performance and move around on that bandwidth efficiency plane and ultimately push us closer into the capacity, achieving the capacity of the channel. So this is our reason for looking at forward error correction. This is our overall looking at a communication systems. How can I manipulate it to achieve the goals of my particular system? And now we're looking at another arrow in our quiver, another tool that we can use to attack this, and that is forward error correction. So forward error correction is very well covered in the textbook we're using in Scholar, and we'll be starting out in Chapter 6 discussing some basic concepts in coding, some introduction to what we do in order to implement codes, what the strategy is, and so we'll start out with time coding and what are orthogonal codes, and we'll find out that this is an idea of how I can use coding, and we'll find out this is extremely spectrally inefficient, but that's okay. It just gives us an idea, breaks into the coding idea. Then in the book there are some channel models in this section. I won't be covering them today. I think you've probably seen them before, but you can have a look at the text for that. I will do a brief discussion of parity, because it is, again, introducing this idea of forward error correction is another way. First there's orthogonal codes, then there's parity, and some vocabulary, code rate and redundancy. So these basic topics are all covered in the beginning of Section 6. And finally, we'll just address what is the forward error correction strategy. What are we trying to achieve, and how do we get there? So in general, coding. Why do we do forward error correction coding? And it's to improve the bit error rate, the probability of error. As I mentioned, that's the pillar that we're trying to improve there. But in order to do it, we have to accept that we're going to have to expand the bandwidth. And so I'll start out again with an example of orthogonal coding, which is like really pays too much for bandwidth, but at least we'll see the concept. In the book they also talk about biorthogonal and simplex, which are a little less inefficient, but still in the same vein. Then I'll talk about parity, and parity is more about detecting errors instead of correcting errors. But we'll talk about that idea, and there are some parity which actually could correct some errors, but mostly we detect errors and we rely on retransmission in order to finally get the error. So we identify there was an error, and then we try and retransmit it in order to get the information correctly. Now, the last part is where we're going to talk about forward error correction, where our goal is to really correct errors. There's two ways, well, there's many ways to do it. One category of codes is known as block codes. Another one is known as convolutional codes. And the convolutional codes can be very good at minimizing the bandwidth expansion. They each have their advantages. In fact, we often combine them into supercodes that combine both. So we'll be talking about the goal, whether it's block code or convolutional code, is to look for good codes. There's just a huge way of applying this general concept of coding. And we want to find a good code is one that improves my probability of error, but it makes the bandwidth expansion not too big. So that's what a good code does. So we'll just talk about codes in general, and then we'll try and get into some examples of good codes as we move on in the course. So, first idea, or some vocabulary. Suppose we're using a block encoder. We'll start with some vocabulary for block encoders. And what I mean by a block encoder is I take some collection of bits. And let's say that this collection of bits is k bits wide. So I have k data bits. And that becomes a block which is bigger because I add some extra bits. And that in the end, instead of being k long, it's actually n long. So I'm adding redundancy. So the way a code works is that I take my data bits, but instead of just sending the data bits, I send extra bits. Sometimes we call them parity bits. And these extra bits are not more information. It's structure that lets me determine if there were errors and also how to correct those errors with the forward error correction code. So at least this gives us a simple way to quantify what the trade-offs are that we're making. For instance, we'll define the code redundancy as being the number of parity bits divided by the number of data bits. So for instance, if I have, suppose I have 2 and I add 1 here, then I would have 1 divided by 2, 50% redundancy in this case. When I talk about the code rate, I would say that this is a 2/3 code, or the code rate is 2/3. Now, in order to achieve this, I'm going to have to put up with a bandwidth expansion. And the bandwidth expansion is 3/2. It's just the inverse of the code rate. And you can, well, we'll be talking about how we come up with this, but the basic idea is if I want to send information at the same rate, I would have to use more bandwidth in order to do that. So if I wanted to send 8 bits in 1 second, and then now I have to send 11 bits in 1 second, well, I have to send it faster, which means I have to expand my bandwidth in order to send it faster. So we'll start with a orthogonal code, and this can sometimes be called Hadamard modulation, and it's to show you the concept of how coding could happen. So let's start with a simple example. Suppose that my data that I'm going to send, I break up into blocks, and again, this is going to be the blocks of k = 2. So what am I going to have? I'm just going to look at binary now. Suppose we have binary modulation. Then if my k is equal to 2, well then I can have a 0, 0, I can have a 0, 1, a 1, 0, or a 1, 1. Those are the blocks that are possible. Now in this code, I'm going to add 2 more bits. Okay, so redundancy is high. I'm doubling the number of bits. And so here's an example. Suppose that I make these 2 bits become 4 bits, and these 2 bits become 4 bits, etc. We call this the code word. here is the block, and here is the code word which is associated with that message block. And then what I transmit over the signal in Hadamard modulation is I take exactly this code word and I just use return to 0, just a simple binary operation. So I would send one level, in this case they're all zeros, so they're all -1, so BPSK modulation. Here I'm alternating 0, 1, 0, 1, so I go from -1 to 1 to -1 to 1, etc. So here I have a waveform that's associated with each one of these messages that I'm going to send. So I take in all of my data bits, I break them into blocks, and when I have this, I send that signal. When I have this pair, I send that signal, etc. So why did I choose this set? Well, let's start looking at what happens when I look at the correlation between any two members of this set of 4 waveforms or 4 code words. And if I look at that, we'll see that the cross correlation and these are piecewise constant. That means that it's either plus or minus 1. So if I say this one times this one, well, I'm going to have a -1 times a -1. That's going to give me a 1. So -1 times a 1 is going to give me a -1. So when I do the cross correlation, I'm going to get, on a per interval here, I'm going to get either a plus or -1. And the total cross correlation for one code word to another is just the number of bits that are the same minus the number of bits that are different divided by the number of bits. It's kind of like the definition of the cross correlation between two code words. And these are chosen so that the number of this cross correlation has very good properties, and I'll show you that in a minute. But let's just cut to the chase and say that I'll show you that depending on the expansion factor, so this factor m, I can get very good improvement in my bit error rate over the standard BPSK modulation. But it's very, very bandwidth inefficient. K bits without coding, 2 to the K bits with coding. So very bandwidth inefficient, but we get a very nice trade-off for it. Well, nice. I won't say very nice because there'll be other ones that will be much better. But an improvement by trading off bandwidth. And that's what coding is all about. We just want good codes. This is not particularly good code, but it is a code. It lets me trade off bandwidth to get better bit error rate. So in this time, we're using what are called orthogonal codes. And when we look at the cross-correlation between the orthogonal codes, we're going to see they're orthogonal. So that cross-correlation is going to be 0, which is why we can easily use them. And what's nice about Hadamard codes is that we can make this for any value of k that we want. We can come up with a way of making orthogonal codes. So we start with the base Hadamard matrix, which is 0, 0, 0, 1. And in this matrix, the way to interpret it is the first row is 0, 0, and that's the pair used for a logical 0. And the second one is 0, 1, and that's what's used for a logical 1. Now suppose I want to take this base Hadamard matrix of order 1, and I want to build from that my first set of code words. So it's a very simple expression. I take my base H1, which is this matrix here, and I tile it. And I tile it in a block matrix where 3 of the entries are the same, and in the 4th entry I put the complement. So here we can see the 0, 0, 0, 1, 0, 0, 0, 1, and then in the last corner here I change it to 1, 1, 1, 0. And if I look across now, this is going to be exactly what was in my list of code words in my first example. So if I said that when I had 0, 0, I had this, which was 0, 0, 0, so that's this pattern across the top. And in the end for 1, 1, which was the last one, I would go 0, 1, 1, 0, 0, 1, 1, 0. So this is how I built that first example that I showed you. And I can just keep going. So this was how I built H2 from H1. And if I want to build the next one up, I would just keep tiling in exactly the same way. So if I wanted to make H3, I would put H2, 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 and H2 complement. And in these, for all of this matrix, why did I do it in this way? Because it guarantees me that for any pair of rows, so for any code words, the number of bits different is always exactly equal to the number of bits the same. So if I'm looking at the cross correlation, as long as the number of bits and the number that are the same, the number of bits that are different are equal, in that case I'm going to get zero cross correlation. So here, between this one and this one, the number of bits which are the same, well, that one's the same, that one's different. These two are the same, these two are different, so 2 and 2, and you can take any pair and you will find this characteristic holds out. So it gives me a way of building a code set so that they are orthogonal to one another, and that allows me, oh, here's the case for k equal 3, and if I were to look at what is the spectral efficiency for these solutions, well, you can see the equation is given here based on M, and it's like any orthogonal modulation. Before we were talking about FSK as being an orthogonal modulation. Well, this is a time orthogonal modulation. So I already found out what the spectral efficiency was of this. It's log 2m over m. I already knew from FSK that it was very poor in spectral efficiency. So this got me a way of finding another way of doing an orthogonal set. So in the first part of the course, we only saw FSK as an example. But using Hadamard modulation, I'm introducing orthogonality in the time domain, which is the same as saying I'm going to cost myself in spectral efficiency. So the log 2m, remember, that is the number of bits in my code, and the m is the number of bits in the code word. And so this is how I get the expansion. So in the same time that I would send 3 bits, I now have to send 8 bits, and that means the bandwidth expansion or the loss of spectral efficiency. So, again, in summary, I could look at the probability of error as a function of m, and really these are the same exact equations I found for FSK, because in signal space it all comes out to be the same. As long as they are orthogonal to one another, these signals, then I have already found the equations which were valid for those, because the signal space representation would again be a hypercube, just like it was for FSK, because it has these same principles. So if I look now at the performance curves, these are the same performance curves we saw for FSK, completely indistinguishable. But the interesting thing is that now I've interpreted as being a coding approach, that I take a block in, I add redundancy, and that leads to an improvement in bit error rate, but at the expense of spectral efficiency. So the whole point of going through the orthogonal coding was to show that we sort of already saw these basic ideas in the modulation part of the course. And this is sort of our bridge from taking an entirely modulation approach, just changing the signal space representation so that we get to an equivalent place. And now we're going to say, well, that's the concept, but let's try doing some optimization. This is like not the best thing we can do in exchanging spectral efficiency for bit error rate performance. So we can do something better. And those are the forward error correcting codes that we'll be studying. So before we go on to forward error correction, one last topic to get over, and that is parity. And in parity, the idea is to identify errors, but we don't necessarily correct them. Very typical parity would be even parity or odd parity. So in this case, it's like a code, and we would say that there were k bits which were uncoded, and I'm going to add 1 bit, which is the parity bit, the traditional parity bit, that I'll add. So for instance, in this case, we would look at 0, 1, 0, 1, 0. So I have 3 zeros and 1 1. So I add a 0, and now the parity is even, because I have I always have an even number of 1 and 0. If I do the sum, if I do the sum, I would get 0. Here, this is the parity bit. I had 3 1s. So if I do the binary sum over those 5 bits, I would get 1. But I don't want it to be 1, I want it to be 0. I want it to be an even number of 1s, if you will. So I add another 1, and now that's the parity bit. So whenever I sum across all 6, I should get a binary result of 0 whenever I do the sum. So if ever I receive a block and I do the parity sum and I get a 1, well, I know something went wrong. I don't know what went wrong, but I know something went wrong. So that's what's about the goal of parity, is to identify that an error occurred. So you can ask, how effective is adding 1 parity bit? How much good do I get? Can I quantify how much better I'm doing? So we can calculate the probability that I will detect an error, or that I will miss detection of an error. So let's look at how I would do that. Well, in probability theory, it's a combinatorics question that I would end up calculating. And so the first question I'll ask myself is, suppose that there are j errors in a block of n bits. How many positions are there? So that's easy. That's n choose j, the binomial coefficient. So n factorial divided by j factorial divided by n minus j factorial tells me in that block of n bits how I could place j errors. Okay, so that's how many blocks have j errors in them. Now, if I say, what is the probability of getting j errors in n bits? Well, I would take the number of times it could occur times the probability that it would occur. So what is the probability of getting j errors? So assuming that, this is the probability of bit error is p, then p to the j, there's j bits in error, and 1 minus p, the probability I won't have an error, would be raised to the power of n minus j. Those are the number of bits which were not in error. So this is a classic calculation of the probability of having j errors in n bits. So when am I going to miss an error? When am I not going to detect the error that I should detect? And that's going to happen when I have an even number of errors. So if 1 bit gets flipped, well, then the sum will go from being a 0 to being the sum is 1. But if I flip 2, then I'm going to get a 0 and I'm not going to detect the error. So that's a mess up. So anytime I have an even number of errors, I'm not going to detect, my parity isn't going to work. I'm going to have an error and I'm not going to request a retransmission, and so the parity won't work. So how often does this happen, the probability of missing? Well, I'm going to do a sum, but I'm always going to look at even number of errors. So in here, it's only 2 times j, and I sum over 1 to n over 2. And so this gives me the probability of a non-detection, not getting the error, not catching it. So that's parity. And so we can analyze the parity and see how effective it is. It is possible to also use vertical and horizontal parity. For instance, we would add a bit so that we could get the parity. So we would put our blocks of data and fill them up like in a matrix. So you take this sequential, and we would start filling them up with 5 bits at a time. And then once we have built our matrix of 5 by 5, we would add parity bits for the rows, parity bits for the column, and then a parity bit for the parity bits. And this allows us to actually correct some errors. So if it occurs 1 in each column and 1 in each row, then I can catch it. So it's a more effective parity. So this is where we sort of bridge the gap between parity just detecting errors and also being able to correct some errors, but you can't correct all of them. Okay, so I'll push aside parity. We saw the idea we could do orthogonal modulation. Orthogonal modulation, that's a way of trading off bandwidth efficiency for bit error rate efficiency, just like we did for FSK. It's just that the structure here we did in the time domain, and we interpreted them as codes. Now what we're going to talk about is real forward error correcting codes. So not using this orthogonal, but trying to find out with some kind of redundancy which is efficient, that allows us to get better performance, but not being so profligate with the with the spectral efficiency, not paying too much in spectral efficiency. So first of all, I'm just going to talk generally now before we get into specific error correcting codes. So let's just look at the bit error rate curve for coded and uncoded systems. So what I see here in the solid curve here is the uncoded, typical. This maybe is BPSK. And what I'm going, so of course it's EB over N0 versus the bit error rate. Now what do you see in the dotted line is now the coded rate. And you remember, it's better if it's closer to the origin. So the coded rate is better because it's closer to the origin. And there's kind of a couple ways I can look at that. For instance, let's look at a compromise where I go from, what is this, point A to point C. Point A to point C is lined up on top of 8 dB EB over N0. So I'm stuck with this EB over N0. That's what I'm living with. If I don't use coding, I'm going to get 10 to the minus 2 of errors. If I use coding, I can get only 10 to the minus 4 errors. So I'm getting better probability of error, but of course, when I use coding, there's going to be something to pay in bandwidth efficiency. Another way I can look at it is how much signal-to-noise ratio do I need for a given quality of service. For instance, suppose I want 10 to the minus 6 as my bit error rate. Well, if I don't use coding, then I'm going to be over here at point D, and I'm going to need something like 14 EB over N0 in order to achieve that 10 to the minus 6. But if I pay the cost of error correcting codes, both in terms of paying in terms of complexity, paying in terms of bandwidth, I can get that down to only requiring 9 dB for EB over N0. And we call that the coding gain. So that's the gain when I use an error correcting code. In this case, it would be something like 5 dB coding gain because I'm using a code. So remember that on these curves, we cannot see what we're paying in bandwidth efficiency. Okay, we can only read on these curves the improvement in bit error rate. For instance, suppose that we're not using coding. We're sitting here with performance of 10 to the minus 6, and I just want, if I go with faster transmission. So I was doing 1 kilobit per second, and now I go to 10 kilobits per second. Because I'm going to 10 kilobits per second, of course, then I'm going to expand the bandwidth, but that would let in more noise, and maybe I would not get good. I would get worse performance. But now I add an error correcting code, and then I can go all the way down to E and get the same performance. So that gives you an idea of where you're trading and how you're getting your gain. But let's look at a specific numerical example to see that. But before we do that, one step before we do that is to look at the place in the curves where the dotted one is not closer to the origin. That there's some crossover region, and that's where coding can actually make your performance worse. So why would I use a code if it was going to make it worse? Well, the answer is I don't use it. I don't use it in this area. I only use my error correcting codes if I'm down here. But you know, why does it cross over? That's one thing we'll see in our numerical example. Oh, by the way, we call this the FEC limit. It's the point for the probability of error uncoded, where if we add forward error corrections, we'll actually get an improvement. We also call this the forward error correction threshold sometimes. So I'm going to take a very simple example. Suppose I have EB over N0, it's 9.6 dB. That's in dB, and in linear, that would be 9.12. So I take this equation for BPSK, and I go and say, well, what probability of error will I get at 9.6 dB? So I'm looking over here on that uncoded rate, and I see that I would get something like 10 to the minus 5 is my bit error rate. Now I'm just going to tell you that I have a code, and this code is special. It turns it into 11 data bits it turns into 15 coded bits. And my little magic forward error correcting codes, whenever there's only one error in the block, I fix it. Every time, doesn't matter where that error is. If it's in any one of these 15 bits afterwards it's transmitted, I'll find it, I'll correct it. That's the way this code works. Okay, so let's just take these numbers. What does that mean? Well, first of all, there's the bandwidth of expansion. When I would normally only have to send 11 data bits, now I have to send 15 data bits. So I have to send it faster. If I send it faster, it takes up more bandwidth. So there's like a 36% increase in the bandwidth. Now when I ask the question, well, what do I get? I'm paying 36%. What do I get? Is there a bit error rate improvement? How would I know that? Just given this data, how do I know if this code is going to actually improve things for me? So we'll go through the math. So what is the probability of having at least one error in k bits when I don't have coding? Okay, so I'm not using any codes. I just got my k bits, no redundancy added. And I want to know, well, how often is it going to happen that I'm going to have an error at all? Any number of errors, one error, two errors, however many errors. But there's going to be an error. That's 1 minus the probability that there are no errors. That's easy to calculate. It comes out to be something around 10 to the minus 4 for this example. Now I want to say, same question, but when I use coding. Okay, first of all, I have to change, because the EB over N0 that I have here, 9.6 dB, that's when I'm only sending those 11 bits. When I have to send 15 bits, I also have to take the energy and spread it over 15 bits instead of spreading it only over 11 bits. So that means that I take a hit right away on my EB over N0, and I call it E coded over N0. So EB over N0 is no code, and now I have to reduce it because of this redundancy I'm adding. So in the case of this code specifically, 11 data bits, 4 parity bits for a total of 15 coded bits, I end up having only 8.3 dB instead of 9.6. So I take a hit because I assume that I have the same energy budget and I just have to spread them over more bits. So for the coded block, for that value now of 8.3 dB, I calculate the probability of error, and now it's something like 1.3 times 10 to the minus 4 instead of 10 to the minus 5. So before I do any correction, the bit error rate actually is getting worse because I have to spread out my energy across more bits. Now I ask the question, I know that a block with one error will be corrected. So the only time that I'm going to get an error is if the errors occur not one but two or more. So now I calculate what is the probability that I will get 2 or more errors per block. And in our example, that comes out to be about 1.94 times 10 to the minus 6. So, did I get coding gain? Yes, I did. In a block of 11 bits, the probability that I would have some kind of error, in this case it was 1 or more, was 10 to the minus 4. But now when I use the coding, the probability of getting some kind of error, in this case it's going to have to be 2 or more, because the 1 is going to be corrected, that's only 10 to the minus 6. So I have like a factor of 60 improvement in my probability of having some kind of error when only paid 36% in the expansion of bandwidth. So we did get improvement. So that means that we're somewhere down here, which makes sense. I said that we were using 9.6. So we're in the good region where the dotted curve really is close to the origin. Now, what would have happened up here? Why would it not work? Why would I have this crossover effect if I'd started up there? Well, the reason is when we were doing this beginning point, our beginning probability of error would have been really, really bad, okay? Because I would be starting over in that other region where there's a lot of errors in the begin with. And then when I take the hit on the coded error, it would really, really be bad, and I wouldn't get an improvement. So it just means that the channel has to be pretty good so that when that first step with the BER worsening, if it gets too much worse, well then things fall apart. And that's why we have a FEC threshold.